It was heroic on a structural mechanics front, it was heroic on a material science front, it was heroic on a power electronics front, it was heroic on an aerodynamics front, it was heroic on the control systems front. It was not a walk in the park on any vector, and it was world firsts on every single front.
Today, our challenge is climate change. We cannot turn away from it. I absolutely believe that we can do something about it. That's what engineers are good at, solving problems, and this is a big one.
You very rarely work on something so open-ended. People believed in the audacity of it, in the individuals and their capacity.
All right, it's you now. Oof. You never know if you're gonna succeed, but one thing for sure, if you don't try, you're not gonna succeed. It's not like one single idea that's gonna solve global warming. It's too big of a problem to be solved by one thing. It's gonna be the combination of multiple ideas from multiple people all over the world.
We got 5 minutes of autonomous flight down.
Is that really?
I don't know, not in a row. And we got 4 dead kites.
Yes, we do.
Very dead. 2 were more dead than others.
I guess I like to think about Makani as we're taking wind turbines and we're thinking about what is the best possible system we can build instead of a wind turbine that extracts wind energy. What's the most optimal system? And then we're trying to build that.
In late 2006, I joined Makani Power as the company archivist. Earlier that year, a team of engineers and kiteboarders had begun experimenting with how to harness wind energy using kites. Kiteboarding gave them a visceral understanding of the power available in the wind, and they wondered if they could replace the heavy steel towers of wind turbines with a lightweight, tethered airfoil. If the idea worked, it could revolutionize wind power. So I set out to document every part of the process.
Andrea. Hi, Andrea. What's the date, Andrea?
It's the 27th.
Yeah, what day is today? Where would you rather be than here?
We wanted to use the simplicity and beauty of kites to make wind power cheaper and more accessible for billions of people. But teaching a kite to fly itself, to fly autonomously, hadn't been done before. And I recorded each test as if it would be the best flight we ever had, or as if it would be the biggest disaster. Sometimes it was neither. Sometimes it was both.
I don't know how that overflew. That was doing loops around the trailer.
Was it sucking the throttle? Is that what happened?
That's one of the things.
Yep, carbon fiber broke.
Oh, sweet.
Oh, wow.
Well, it wasn't meant to go back. There's a stop.
Yeah,
Yeah.
I didn't think that was possible, what it just did.
Well, I thought you were going for a 360.
Well, I mean...
Kites are actually a technology that we as humanity have had for centuries, right? We've just never applied it to generating power.
Makani's project is a little bit unique in aerospace. There are plenty of airplanes. There are not many airplanes tied to the ground with a giant tether.
We have over 100 years of history in aviation. When the Wright brothers first started to fly until now, we've been able to do so much more things in aviation, right? We have jets and propellers and airplanes with wings of all sorts of configurations on planes, and we've been to the moon, but we have never in that whole time tried to develop this aeronautics and aerodynamics that happen in this type of kited flight.
We're trying to solve one of humanity's biggest problems, which is how will we sustainably generate energy in this new world where energy usage will only go up from here. Nothing good will come easy in the energy space. That's a big challenge, and that gets me out of bed every day to think that we're trying to solve a problem like that.
There's a lot of different ways to make power. You know, you can put hamsters on treadmills or solar panels on everything. The real question is, what's it going to cost you and how much energy is it going to give me?
So when we started Makani in 2006, we hadn't yet really had the fracking boom. That was just starting. So natural gas wasn't as terrifyingly cheap as it is today. And wind energy was about 20 cents a kilowatt hour, which is super high. And we were able to convince ourselves on a napkin that we could produce electricity with something that looked like Makani for 3 or 4 cents a kilowatt hour. And if we got lucky, a little bit cheaper maybe.
The physics that convinced us kites were a good way to generate electricity came from a paper written in 1980 by Miles Lloyd. Lloyd's idea was that a kite could fly across a greater area of the sky and generate more power in a unit of time than a wind turbine fixed in place.
Wind turbines produce power by slowing the wind down and converting its speed into energy. There's a certain amount of power available in a given area of wind. Wind turbines produce close to the maximum possible power from the wind in the area the blades sweep through. To make more power, they need to grab more wind, which means getting bigger and more expensive to build. Kites can expand this limit, but a kite flying downwind doesn't make much power. To maximize power production, kites, like wind turbine blades, have to move across the wind. This is the same way a sailboat works. A sailboat moving across the wind redirects the wind around the sail and creates two forces. One force leans the boat over. The other force pushes the boat forward. Only the forward push moves the sailboat along. The blades on a wind turbine work the same way, redirecting the wind and creating one force that pushes on the tower and another that pushes the blades forward. The forward push of the blades turns a generator to make power. A crosswind kite is like freeing a blade from the tower. A freed blade, now a wing, can grab more wind, making more power than it could while stuck on a tower. We need a tether to handle the force that was pushing on the tower, and a tail to control it, and generators to turn that forward push into power. And now we have a crosswind kite that can grab more wind and make more power for the same size wing with less materials, enabling access to wind energy in more places at lower cost.
We had a long way to go before our kites would be sophisticated enough to bring the cost of wind power down.
One kite good, two kites better.
But each experiment was a step forward, and no ideas were off the table.
Hey, can someone come give me a hug?
The problem we were trying to solve was serious, but it helped if we didn't take ourselves too seriously.
The place Makani started was with soft kites, with essentially kite surfing kites, and with generation on the ground using a winch. And this is actually a great architecture in many ways. It's very quick to prototype. It's a very simple system. So it's possible to iterate and test, and iterate and test, and iterate and test. In the realm of innovation, this is key because you can only learn so much from simulations. At some point, you just really have to interact with reality. After a while of looking at these soft kite systems and developing up a simulation capability and analytical capability within the company, we found that the promise of rigid wings, of a rigid wing architecture, was much higher. This leaves a big problem, though, of how do you get the thing in the air. We started by building actually what was a very complex wing, and it was almost the exact opposite of the very quick iterate and test that's possible with the soft kites. We went ahead and built, fully off of simulation, a very complex system. The problem with this is that there's no interaction with reality. So all it takes is one mistake by one person to lose a device like that. That's not a great way to prototype. That's not a great way to make progress.
It took us 9 months to build our first rigid kite, and we only made one. For a team used to flying and exploding soft kites, having only one prototype felt like not just a bold step, it seemed reckless. For a couple of months, we hovered it under a safety constraint line out near Santa Cruz until we felt like we were ready. Oh. 2.6 seconds of flight. As the 9-month kite splintered, we were humbled by how much we had to learn. The failure of our first carbon kite hit everyone hard, but a few folks on the team had been prepared for a setback like this.
So at about the time that we were getting near finishing this first very complex rigid wing prototype, we started a much simpler, faster test program.
Okay, I guess we're ready.
Focused on iterative testing.
That was high. Bam!
The day after we crashed the 9-month kite, we tested the cheap one, and it flew. Watching the kite loop successfully, we knew we were on the right path to learn all the things we'd need to know to harness wind power using very few materials.
I should be frowning right now.
What are you doing instead?
I mean, it's kind of funny. So is that part totally intact? Everything's perfect. Yeah, nothing on this broke. So, that's awesome. Yeah.
Okay, let's do voltage check on constraint release.
The next prototype we built was Wing 6, which was itself a little homely, a little hacky, held together by guy wires and tape and made of styrofoam.
Okay, burn it.
We had committed to a rigid kite design with onboard power generation. And Wing 6 was built to help us work out some of the trickiest flight maneuvers we had to learn to control. Hovering to launch, and then transitioning to crosswind flight, the kind of flight that would generate power.
Tension is at around 35,000. Still good?
Nice. Freaking awesome.
Okay, here we go.
As ugly as the kite was, the transitions from hover to crosswind and back had worked. Pulling together a prototype to test quickly and cheaply had paid off. The heart of Makani was always evident in the shop, where coffee was shared, music blasted, things were created and fixed. The lines between engineer and artist, between friend and colleague were blurred. As we invented new technology from scratch, we also needed to develop a common language. Manho was a master craftsman originally from Korea who had made and flown experimental composite aircrafts of his own design before coming to Makani. Tommaso was an incredible fabricator and engineer who had heard about how we were trying to solve climate change using kites and risked everything to travel from Italy to San Francisco. He enrolled in language school, where it would turn out that he met his future wife, Anita, who also eventually worked at Makani, and learned enough English to knock on our front door and say,
"My name is Tommaso Romanelli.
I want to work here." At the end of each day in the shop, Tommaso's blue gloves would be covered in Sharpie, scraps of song lyrics and slang he'd heard and worked to understand.
Professor, what's another name for pirate treasure?
Working on hardware was another kind of language, translating the invisible idea of fighting climate change into something we could see and feel, bringing us hope, bringing us together. Tommaso and Anita weren't the only couple in Makani's history, or the only set of forever friends. We'd started out building a kite, and along the way, we'd begun to build a family. We'd been iterating quickly with cheap materials, and we'd arrived at a design that worked. It was time to build a robust prototype that could scale into a product. With rotors and generators mounted on a rigid airframe to launch, generate power, and land, Wing 7 would generate 20 kilowatts and would demonstrate all the modes of flight needed for commercial operation.
Tarek, this is the first ever assembly on the runway.
It's just gonna work. It's gonna be so easy. Did I just jinx it?
To support onboard generators and higher flight loads, we had to risk the time, effort, and expense of building the new kite out of carbon fiber, something we hadn't dared to do since the crash of our first carbon prototype. But this time, we had real-world data to inform our design, and we'd secured fixed-term funding from the U.S. Department of Energy and Google.org. Even with more data and adequate funding, we proceeded cautiously, flying the kite under a safety constraint line to make sure all its subsystems were ready to work together.
3, 4. That's going. That wasn't bad, eh?
No one had ever controlled an aero device like this before. A rigid airframe with the extra dynamics of being tethered to the ground that would fly like a quadcopter and then as a kite.
Wing 7 returns the ground in one piece.
But the day came where we couldn't learn any more with the kite safely tied into constraints, and we had to fly it for real.
If the wing were to start coming towards us, we'd only have a few seconds to react. Does everyone have a plan for where they'd go? Something to get behind? Last flap check.
Flaps look good.
Pilot to pilot hover mode.
Pilot hover.
Wind check.
Green. 6 meters per second.
Stoplight check.
Green.
Starting data acquisition. E-stop ready?
Ready.
Pilot ready?
Ready.
Begin test.
Okay, burn.
Confirm.
Burning. Dan, go.
10 meters above the fire truck.
Solar.
Auto hover. Axle 1. Axle 2. Transition in.
Tension.
It looks like an airplane. It's not an airplane. It's an airplane with a string that changes directions constantly. Nothing's ever still. Nothing's ever steady.
It's a little ugly, but okay.
Still good, 80.
Someone's watching the time, right, Eric?
I think it takes one part bravery and one part blind optimism to keep your prototype in the air when your flight looks this bad. But we managed to hold on and not only fly our first loops, but perform our first transition out of crosswind and back to hover. This maneuver, called Trans Out, was one of the trickiest controls challenges our system required.
Beautiful.
The motor temperatures are high. Motor temperatures.
For our first flights, after Trans Out, we would release the tether and pitch the kite forward into a glide landing. Later, as part of our quest to make the whole system automatic, the plan was to have the kite land vertically on a ground station.
14, 13, 12, 12, 9.
We'd successfully flown and safely landed Wing 7. The effort we put into iteration and testing had paid off, and we had a working carbon fiber kite that we could control. This felt amazing, but we had plenty to learn about how to fly gracefully and effectively generate power. I can tell you, it wasn't an overnight success.
We were
were trying to extract power from the wind. And that's what we would get closer to when we went testing. It's like the actual wind, the physical world where our technology had to work well. So sometimes the challenges were it was not windy enough and we were sitting there waiting for wind, and sometimes it was too windy. Being with the small team of people, like group of people who maybe we just got lucky or we have selective memory, but like generally like they got along pretty well. And you have a ton of work to do because you have to set up this thing. You have only so many hours before the sun sets and your opportunity for testing is over or your test day is over. There's like one unified goal for everyone, which is like, let's launch, let's fly.
No, I was really hoping there weren't any snakes here.
It's a gopher.
It's not a rattle.
Yeah, let's check. Let me just make sure with. Oh, I Google search baby rattles.
Flight testing was like an itch that we had to scratch. Our team was motivated broadly by climate change, but in the everyday we got by with silly rituals, celebrations of small success, and lots of coffee. Around this time we coined the term flangry, which is how we'd feel when we hadn't flown in a long time. This kind of anxious hunger for progress. As we put hours in the field, things broke, motors overheated, the controller was always being improved. But everything that failed taught us which parts of the system was weak. We fixed it, we moved on. It was tedious, but we inched forward, making real progress. Then, just in the middle of our cadence of setting goals, meeting them, and setting even harder goals, Corwin, our CEO and one of the founders of Makani, died suddenly and unexpectedly. He had hired most of our team and shaped it. He had baked us bread and made us salad and laid out milestones that were just the right level of difficulty to keep us steadily moving forward. We didn't have to ask ourselves what Corwin would want us to do next. It had always been clear that Corwin was driven to make Makani succeed as a part of the way he cared for people and the environment. With Corwin's death heavy on our hearts, we began preparing for our next big flight goal, all modes. The kite would launch, transition into crosswind, fly loops, and transition out of crosswind to land back on the perch. Coupling one complex robot to another and generating power in between was something no other kite team had ever accomplished. The new ground station would have three main jobs. It would serve as a perch for the kite between flights. It would manage the tether during each flight mode, and it would connect the tether to a ground power system, allowing electricity to flow to and from the kite. We'd spent 6 years learning how to control a kite independently from a perch, so teaching our sky robot to interact with a ground robot would take a little time. We reached a point where we hadn't eliminated all the risk from launching and perching on the ground station, but we needed to test all of the modes of flight together in order to learn more about how to improve the system. We'd been pushing this challenge down the road for years as we solved other hard, but not as complex problems, and we couldn't punt it any further. Getting the kite and ground station to perform a complicated controls ballet together was possible in theory, but we had to test it.
Goal number 1, not crash. Goal number 2, take off and land on the perch autonomously, fly crosswind in the middle. Goal number 3, not crash. Goal number 4, make power.
XL1. Jensen.
It's good. It's good.
Let's crosswind.
So looks good. Looks good. Looks good. Looks good.
Wow, it's beautiful.
Looks good.
What are your tensions?
A few more loops like that. 5,000, 6,000. You get up to 10,000. Everything's looking good to me.
It's it also looks like it's flying way slower.
Okay, so now it's trying to go higher. Okay. Close at it. This is the highest it's gonna get.
17.
That is barely flying.
Alright. And it's gonna come down. It looks good.
Wind
Looks
is
good.
7.8.
Oh, it's very close.
Trans out.
Trans out.
Okay, keep close at it.
Alright.
Okay.
It's a lot of roll.
Let it come back.
Watch it.
Things look good here.
Okay.
Everything's green.
Everywhere out here.
Things look great here.
You want to bring it closer before you slow it too much? Yeah. We're not even there yet.
Bring it right. Okay, I'm starting to see the tether now. It looks low. Looks good to me.
It does look in this part.
Yes!
Well done.
Hey guys.
Hell yeah.
That was sick.
Next, we're flying for 10 hours.
10 hours of awesome.
Yeah, 10 hours of awesome.
Working on something hard for a long time as part of a team and watching it work exactly as you had intended it to is as good as it gets.
I think that was amazing. I'm really happy with the results. I wish we would do it again, but there's no reason to today. Let's just celebrate.
It just kind of reminds me at least like how freaking awesome what we were doing is.
I love my job.
Now that we'd proven it was possible to get the kite and ground station to work together, we went on to get flight hours. Accumulating hours in the air would teach us about the reliability of our system and would help us uncover bugs that we could refine in our future commercial kite.
I think we're gonna go for 10 hours. You know what a gopher is?
We're not gonna.
The more we flew, the more we learned.
No, we're gonna go for 10 hours. We're gonna go for 10 hours. Sometimes we achieve what we attempt.
Flight testing took a tremendous amount of effort, but that effort led us to better designs. Troubleshooting, swapping components in the field, and managing the ensuing operational and risk decisions took time. But we gained information from the real world that we couldn't have learned through models and simulations alone.
So that means it'll be sometimes it's thrust and sometimes it's...
Yeah, sometimes it'll be thrust and drag, and sometimes it'll be like both. You're in such deep drag already that both of them are still drag.
Okay, so sometimes it will even be thrust and drag.
Even though Wing 7 could perform all of the modes of flight a commercial system needed, we were going to have to generate a lot more than 20 kilowatts to make a meaningful impact on climate change. We needed to build a bigger kite, and we needed new investment to make that possible. We found the visionary support we were looking for at Google X, a newly formed home for ambitious moonshot projects that aimed to use technology to solve big world problems. At X, we would have the resources we needed to scale up to a utility-sized kite that would get us closer to expanding access to renewable energy for billions of people around the globe.
So we plan to build a 600 kilowatt system. That's enough to power about 300 US homes.
We've spent a lot of time in the prototyping stages in inventing the best device we can, and now it's time to scale up and start building utility scale devices that can make a real difference in the world.
Makani decided to take a big step from the 20 kilowatt Wing 7 to the 600 kilowatt. And so we were designing and building it for probably about a year.
Like most things in life, it's the transitions that are the hard things. So going from hover to flight, going from flight to hover. You know, I think a lot of the last year was sort of lots of little efforts going on, and it was hard to see it was all going to come together. So this was the building year, you know, and the growing year.
When I got here, we were really focusing on design. And we ran into so many hurdles. I don't know if hurdle is the right word. when the hurdle is 3 meters high, it's not a hurdle anymore. But we kept on going at it.
So I'm a little worried that this whole thing's gonna pull down, you know. Okay, let's see, what else do I need to do here to make this look really pretty?
Doesn't this look crazy?
It looks just like week 7.
Only giant.
It's amazing.
No, we're smaller. It's the same size.
You guys are all the same height too. It's kind of amazing.
We started testing with a pretty small subset of what would make the whole system. Like the first kite that we tested didn't have any flaps or any servos for the ailerons. I think it didn't have a tail. Definitely didn't have an empennage. So we had the wrong wing, the wrong motors, the wrong power system on the ground. But yet everything was similar enough that we knew we would start learning by like going out and testing it. And so for a whole year, there was this cadence of integrate the next new system that's ready, so the new motors that we knew were the good motors came. We would spend a couple of weeks switching them and then go back out to test and test with new motors. The next time we go out, we had a new inverter on the ground. And that took a while. That was like a year and a half of continuous integration and testing. But I don't think it could have gone any faster. I think if you had tried to like complete the system and then put it together, there was no way you would get it to go.
After a year and a half integrating new hardware and hovering under constraints with our first utility-scale kite, we were ready to test the kite in crosswind. But we'd found multiple issues with the new scaled-up ground station. We would have to send the ground station back to the drawing board. That kind of design and fabrication would take the better part of a year, and we didn't have the time. Our team, our funders, and the climate, none of them could wait another year to learn everything that crosswind flight would teach us. While one team split off to begin designing the next ground station,
this faces out, right? The GSG is like so.
Another team created Container Henge. A break for a second. One of the things that made Makani fun on the daily was the vocabulary we coined. Objects, procedures, people were adopted and became part of the team. At one point, we had a lot of employees named Jeff. So we had Jeff, Rocket Jeff, Laser Jeff, and just Jeff. Then, Rocket Jeff made a box full of electronics for the M600, and we started calling it the Rocket Box. Even when the Rocket Box wasn't working, which happened, we still had good feelings about it because it was named after Rocket, and everybody loved Rocket. There was a special move we'd do to the kite to make it safe for people to walk around, and we called that the Nicholas, because Nicholas thought of it and wrote the code. Anyway, so Container Henge was one of those things with a special name. Container Henge was the quick and dirty solution to our ground station woes. Made of 2 stacks of shipping containers, it was a remote perch that would allow the kite to launch and land at full tether length, temporarily eliminating the need for the complex hardware that would manage the tether as it reeled in or out. We retrofitted the kite with perch pegs to spread the wing's load across 2 stacks of shipping containers. Nets on top of each platform made it easy to eyeball the kite's position on the perch and helped prevent the kite from sliding forward with the tug of a heavy 500-meter tether. To keep the kite from pitching forward on the perch, we attached a tail spike that would catch on cables spanning the gap between the 2 stacks of containers. In relatively short order, we'd created an uncomplicated ground station that would get us to crosswind faster. The next step was putting it together with our crosswind-worthy kite, SN2.
So we spent the last year hovering serial number 1. And right now, as we speak, Paula is spinning motors on serial number 2 in the Birdcage, which means our crosswind-worthy wing is about to roll out of the Birdcage, and we're about to switch over to hovering that one, which is one of the last steps in the process of moving to China Lake.
We're gonna lift that beautiful new wing over there. We're gonna hover it for the first time. And it's all gonna work.
then we'll do that a few more times and go to China Lake.
China Lake was a remote test site in the desert where we would be able to fly the kite at full tether length for the first time. Before we moved there, we needed to hover the new kite for 16 hours to ensure its hardware was reliable enough for crosswind. But early into our hover regime, we started uncovering bugs. Finding and solving bugs wasn't new, but this time it was different. If we didn't move to China Lake and fly crosswind by the end of the year, we could face a dramatic scaling back of support for our project, or even outright cancellation. Then there were some new oscillations of the pylons. The kite would basically resonate when the motors turned a certain way.
Do you want me to do which one we had today? Yours that goes like this. Right. Like this. I don't even know if this one could possibly be real, but that's what it looks like from the footage.
And then what do you do?
We just lower gains. Just keep lowering gains.
Just as we neared completion of our 16 hours of hover, we were suddenly playing whack-a-mole with motor issues. First, a motor controller fault caused the kite to drop on constraints.
Something just stopped. It stopped and fell.
That's a drop.
That is a drop.
We solved that problem, but in the next test, the starboard bottom outboard, SBO, motor didn't spin, and it wasn't clear why.
The starboard bottom outboard is not spinning.
I didn't like calling what happened a failure.
We all have to own the system. When it falls out of the sky,
Yeah,
like,
but
those quibbly details are...
16 hours was just enough.
So I was working on the last log of the day on Friday.
We had to decide whether to delay further or accept the risk and head to China Lake.
It's like the Metrodome, like when you come out of the chute.
Did you decide anything?
We decided to do the swap.
What about going to China Lake, though?
Well, I don't know if I'm allowed to say it. We're going forward with the move, besides possibly the wing, because we might want to debug this, so the move is going forward as is because so many people are committed to it and schedule time is committed to it. So we'll pack everything up, move, take the wing to the Birdcage to do any debugging if that's the case, if we need to, and then move the wing maybe later than it was scheduled to move.
We had an unresolved motor bug, but we decided to risk it and move to the desert to fly crosswind.
This sort of calculations, like this kind of risks assessment before a launch, were a huge part of flight testing. Every single flight, we were assuming some risk and going into the calculation of like how much of a big deal is this and is it worth the possibility that we lose a kite or that we delay the test? Is what we're going to learn about everything else worth taking this one risk? If you assume the risk, there's a chance you learn very little because you crash before you actually get to crosswind or some bad deal. But you're going to learn something. Like your chances of learning, which was always really our objective, are higher if you assume the risk and fly.
Look at how not dusty it is right here. We spun up. You have to do it the other way also, so because you have to put the box in here.
The farmer tent?
Oh, yeah!
that was an hour and 10-minute flight. With the other flight today gets us our hour and 15. We need to go to heavy tether test tomorrow morning, so we're going to lower the wing, put on the trailer for the night, possibly do a little bit of heavy tether setup for tomorrow.
Great work, everybody!
Yeah,
great day!
Yeah, China Lake's awesome. It's really beautiful. We hovered, it all worked, even with wind coming from the wrong direction. Yeah, I feel like we're like 2 tests away from flying crosswind.
Makani, teamwork, everyone like, you know, picking up their own individual grain of sand towards a common goal. Are you recording right now? Is that one gonna squeeze through? Oh, well, don't try and go at the same time. Oh no, they almost died. Yeah, this guy's like pulling. You're getting some guys under it pushing.
See, he's the crane operator. That's their Ken.
Tomorrow, for the first time, we'll fly a 737 size kite without the safety harness. So it's a big day.
Ready? Don't get too excited, too bullish.
We'd lifted the kite to the perch the night before, and the only thing remaining between us and crosswind was a routine mechanical check. But overnight, the kite had shifted, collapsing onto one of its perch pegs and splitting the trailing edge of the wing. We needed to demonstrate crosswind flight before the year's end, and a true repair would take time we didn't have.
To fix this is to fly next year. It's true.
We had to go for it. We replaced the crushed tip of the perch peg and used rivets to quickly seal the wing.
You're ascend. Keen is ramping. Back.
There's only one moment of launch. It gets really intense around that point in time and space when we're like finally taking off.
Port bay flight. That was clear. Altitude is 11 meters.
Launching and landing from container hinge was challenging because it's made out of big metal objects that can damage the kite if the kite were to hit them, and because it's in a particular direction. So it requires that the wind be blowing that direction consistently.
Our simulation got us a long way, but some things you never anticipate until you actually fly. The first time we did everything, we didn't quite know what could go wrong. We had some ideas, but those first flights are all about learning the shortcomings that only the real world can show you.
Tension is 10. With plenty of tension.
We had checked everything we could check. We had simulated everything we could simulate, but you know, you always wonder, like, is there something you didn't consider or something's gonna work differently?
Altitude 150. Number 4 still. We're in Excel. We're in Excel. We're in transit. We're in transit.
Pushing forward.
Climbing. Looks straight. Looks straight. Looks straight. Looks good. Looks straight. On tether. Looks straight. Looks straight. Looks straight. Looks straight. There you go.
I still sit.
Looks straight.
Making a turn.
Looks great. Crosswind normal. We're in crosswind. We lost the tether. We lost the tether. Released. Wing safe.
Tether's clearing.
Turning right.
Just a little bit, not too much.
Love it when it starts.
Data's good. Keep a right turn coming. Right turn coming. Start turn, left turn.
All the way left. All the way left.
Left rudder.
Left rudder. We still have good comms.
Keep it coming.
I don't
don't think we're making the radial.
Making it.
I'm going to turn into the winds. If I can turn right.
18 meters.
Trying to turn right.
Sorry, 35 meters, 30 meters, 20 meters.
20 into the wind, call flare.
Over your wings, over your wings. Stretch your flare, stretch your flare.
We still have 4 pylons, you guys.
Wow. Nice.
We'd flown unconstrained and brought the kite down safely, so in our minds, the first flight had been a partial success. When we scaled up the kite, we had designed 2 kinds of new tethers. One with a solid carbon fiber core, and one with multiple carbon strands. The solid core was lighter, and it had performed well in lab tests, so we'd flown with it first. But in the real world, it failed before we'd made our first crosswind loop. Learning that it didn't work as well as we'd hoped was a valuable lesson, but not a lesson that would guarantee the continuation of the project. We still had to fly crosswind. Luckily, the stranded core tether was ready and waiting to test, so we fixed the trailing edge of the wing, spooled out the new tether, and got ready to fly again.
The forecast is not very much wind at all. Small chance we catch it on the way up. Probably also late in the day.
Shall we? Or are we afraid?
Oh, well, we're definitely afraid, but we also have an opportunity.
Yeah.
I think we should do it.
We should do it.
Okay, let's do it. It's 22, that's the right number.
Ready?
Ready.
Throttling up. Watching the wind.
4, 5, 6, 7, 9, 8.
We're in ascend. Gain is ramping. Motors are alive.
Tail's clear.
Here goes the noose.
Wind looks good.
Okay, on the
Gain ramp is complete.
starboard side's up. Okay, shooting the gap.
Good in the needle.
And it's 50 at 4.5 meters per second.
Clear platforms.
Altitude is 17. We'll ascend.
Oh, it's cool to look out the window. Okay, throttle is 0.5.
Altitude is 21. We're in hover full length. We're in hover full length. We're waiting. We're gonna translate the correct azimuth. We're in Excel. We're in Excel. We're in Transin. We're in Transin. Looks good. Looks very good. Looks very good. We're right on this other sphere. Looks good. We're in crosswind. We're in crosswind.
30 kilonewtons.
Looks good. Looks good.
It looks good. Awesome. D-twist is following.
We're at 3 o'clock.
Making the bottom.
We're at 6 o'clock.
Climbing. 9 o'clock.
Looks good.
Now it's 9 o'clock.
Our speed went up to 50.
31.
Top tension was about 60, 80.
And that's our first loop.
Okay.
That was top. Bottom speed or lowest speed was 35. We have 2 loops.
Finished our second loop.
30 meters per second over the top.
Tether current did reverse, I think.
Does that mean we just generated?
Maybe.
Clear the bottom and climbing.
Once we got into crosswind, we still needed to get out of it.
Hover is well understood and crosswind flight is well understood, but the transition between them isn't. In crosswind flight, we're flying circles. The kite is flying like a glider on a string. And then to transition out, we need to basically stop the kite. We go from having a situation where the wind is pushing the kite along and generating power to one where we have to stop the kite and use power to hover. And we also have to do this while making the turn. So it turns out these are hard to do simultaneously.
33 meters over the top. Meters per second at 412 meters.
I don't think this is going to be it. Crosswind circle looks good.
That's a different looking circle.
Yep.
Yeah, this is different. It's doing it.
Yep, this looks like it's weird.
Yep.
It's going for it. It's going for it. We're in hover trans out. We're in hover trans out.
Woo! Very pitch back. Working downwind. Looks okay. Looks stable.
It's not coming
Do
down
you want to give it tension command?
Max pitch back.
Roll is 35, 40
Pilot
degrees.
over. Pitching back.
Roll is 50.
Wind is 10 meters per second from 60
Going to auto.
degrees.
meters.
Here we go.
30 meters.
Here we go. Tether's on the ground. It's just correct.
20 meters, it got it.
Right.
Oh my goodness.
What's my mode?
Mode is hover full length.
Okay.
Wow, that was
0.79 on the throttle.
When we saw ourselves falling toward the ground and almost hitting the ground after trans out, we thought, are we doing this to ourselves? Is it just a control law problem? All of these mysteries were there to be found in the data. From a control law's perspective, you can't just be a traditional control law designer here and apply the same old airplane feedback that you do anywhere else. This machine is different, and it demands different sorts of behavior.
The test site was set up for wind blowing in a particular direction. If the wind was blowing in a different direction, we had to fight that wind as we landed in this particular spot, getting the kite to land between these big metal containers, hoping that there wasn't a big gust at that moment. Roll is -10, it's recovering. Roll looks pretty good, it's getting worse, -12, 14, it's recovering. Rolling. Recovering.
I might wait out this gust.
Roll is recovering.
Okay, once that tail's in there, I can't really do it. Ascend. Tail spike's gone. Tail spike's gone. Ooh, that changes things. How do you guys feel about a glide action? So we can land on the perch. It's just going to do a face planter.
Are you sure it's gone?
Yeah, it's starting. I think glide landing might be better. I think because it worked last time, we should do it again. I think that if we had improvement, it's possible.
Everything looks good. Wind is 6 meters per second at -45 degrees.
Okay. I'm going to get over the perch, and I'm going to go back to auto.
Okay, you're in descend. You're in ascend. You're in ascend.
0.56, 0.52.
Altitude is 36 and climbing.
It's moving downwind fast.
We're in Excel. We're in Excel. We're in Excel. Full throttle. Full throttle.
Yeah, throttle up.
We're in transin. We're in transin. It's looking good. It looks good. We're coming off the sphere, but it still looks good. It looks great. It looks really great.
It looks good.
We're in crosswind normal.
I forced it.
We're going to clear the wedge.
Diving.
We're in the... Does not look so good.
Looks good. Clear bottom. Clear bottom.
That was a walking circle, but it's recovering. We're at 6 o'clock.
Okay, at 2 o'clock we're releasing. Everybody ready?
I am ready. Left turns.
Here's 9 o'clock. 10 o'clock. 11 o'clock. 12 o'clock.
Okay, ready?
1 o'clock.
Releasing.
2 o'clock.
This is true. Auto glide's on.
Auto
glide is on. Left rudder. A little bit of left rudder. A little bit of left rudder.
Altitude is
Got a visual on
270.
window. Right rudder. Right rudder. Neutral. 40 meters.
40. 30. 20.
Meters. Make sure you're level. Level your wings.
10, 9, 8, 7, 5, 3.
It's one thing to make the simulation fly better. It's a whole other thing to see the actual kite behave.
We'd finally done the thing we'd been dreaming of for a decade. We'd swept broad loops across the sky with a kite the scale of a wind turbine blade. There were certainly things to improve. But we'd achieved a world's first for airborne wind energy, and X had agreed to continue support for the project.
So we were We were just ecstatic when the kite flew for the first time, and it flew pretty good. That was like a major milestone. But after our first flight, then we got back to the office and we looked at all of the data and we saw things that could be improved. For example, we saw that the kite wasn't tracking the intended flight path perfectly, or the angle of the nose with respect to the wind wasn't quite what we wanted. So we thought about how we could fix this, and we came up with some ideas. We tested them in simulation, and then we went to the next flight test and checked how our ideas worked in reality. And through this iterative process, we were able to make it better and better.
We're gonna lift the thing, and then first we're gonna put all the things on the thing, and then lift it, and then we're gonna pray for wind, and we're also gonna do a lot of rehearsing this morning. And then we're gonna fly this direction, hopefully for 2 hours. We want to land on the perch, that's the main goal.
What did I miss?
We're having a meeting.
Let's do it.
Toss in. This is going.
Looks good. Very high top of the loop. Bottom of the loop.
So.
Nice.
Covering.
5 meters per second. I can see it. Looks like it's a short real color. They were committed. 4 meters. Position looks great. This down.
We began a steady cycle of flying, reviewing data, making changes based on what we learned, and flying again.
We flew from there and ended up there.
Even if we weren't tied to a tether, this would be hard. Our flight vehicle never reaches a steady state in crosswind. It's always turning, it's always accelerating, it's always changing speeds, it's always changing directions. Nothing ever calms down. From a controls perspective, it's a very daunting task because we never have the opportunity to sort of center ourselves, get the kite steady, establish an equilibrium, and do science. Everything's always changing, everything's always accelerating, everything's changing direction. I can't think of vehicles that fly like this. We're shaped like a glider, we're making turns like a fighter jet. It's an unusual machine.
Our flights got longer, our loops and transitions got smoother, and we were learning how to make power. But no one expected things to work perfectly all the time.
Increased turning power.
Oh, what just happened? We got a UPS alarm.
We're still flying. We're still flying.
We're still flying.
I don't know what this is. Keep going.
Motors
continue.
are. Oh, we lost MV. It's a release, right?
Oh, we did?
We lost MV.
Yeah, release. Release. Oh.
Alright, here we go. Okay, you're at 98 meters, 33 meters per second, 40 meters, 21 meters a second.
A rapid upswing on onboard generation had flooded the ground power system, giving the generator on the ground the signal to shut off power to the kite.
Here we are. Welcome to Earth. Okay.
Let's go to the bit of a faceplate, but
We didn't relish having to glide land, but the test had revealed an issue we hadn't foreseen. And once it was fixed, the whole system would be more robust.
I was very tense at the beginning of that flight, but then it looked pretty good. And then it didn't look as good, but I don't know. I think we learned a lot today.
Can you just describe a little bit what was a memorable moment from today?
Probably that part where I had to release and try and fly it. It flies surprisingly better than the sim, so that's a plus. You know, if you're gonna find something out in an emergency, it's nice to know it works better than it's supposed to.
We'd already shown it was possible to glide land the kite, but this time the kite's nose had pitched forward into the desert floor. Even so, the landing gear seemed to have protected the kite from serious harm.
This one is crazy. You can see
that the bond on the mount is really good. So interesting how this crumbles.
Yeah, I designed the landing gear, and I think I very explicitly gave it a 60% probability of success if we landed it in the criteria that it was designed for, which is a very narrow little box. Well, I mean, we are trying to land something that weighs as much as a car on 2 BMX wheels. So that is every bit as crazy as it sounds. Not having to make a new tail surface is nice.
A beautiful case before. Yep. Consider this case closed.
Obviously, it did not meet the entire success of having only 4 rotors and the landing gear to replace. Success is a very gray thing to define. I mean, not everything, most things, very few things are binary. Did it take enough energy out that it prevented an entire rollover? And did we at least save smashing the tail? I would call that some level of success.
Today is the 1-year anniversary of Flying Crossing.
It's a very nice bond line, whoever did it. I guess it was a team effort.
We fixed the ground power issue and we fixed the kite, but we'd waited months for a new tether. And even though our hardware was ready, we still had to wait for the wind to cooperate.
What are we here to do today, Luis?
Oh, you know, what we've been doing over the last couple days. Setting up and waiting and taking it back down again. And starting over again. Hopefully the wind gods come today, right?
We're gonna fly. RPX-08, take 3. Like 2.5.
All right, we're 7 and 10. Let's do it.
There are sentences about Makani this year that absolutely could not have been possible last year. I mean, you can't say anymore, they're flying, but they're not making any power. Or they have a machine, but they're not flying yet. All of these have gone away, right? We've demonstrated that the product works, that we can make power, that we can do it reliably, that we can fly over and over again, that we can have mistakes and recover gracefully. It was a huge year.
But what we're trying to do at Makani is to create a whole new technology from nothing. And so to accumulate the adequate degree of experience and reliability and to be able to demonstrate to investors that the system will have long-term solid performance and economic value, that's really hard to do. It takes a while, and you have to have determination and stick-with-itness to get through those challenges.
We're -8, we're -4, we're coming in. Whoa. Here we go, get ready.
Okay.
Forcing
5 meters, 4, 3.
Starboard wingtip is very close.
I think it's down. We're 1 meter.
Okay, tail spikes in the right. Sliding forward.
Sliding. Okay, it looks like we're down.
It's awesome. I mean, right back waiting for this for like 5 months. And
What was
RPX-08 was our last successful. We've waited a long time for this.
I was like,
oh wait. And we got it. We waited just the right amount of time. We flew, and now we're down, and we're ready for 09.
What runs with 09?
It'll be fine. It'll be just fine.
It looks great up there. So far, so good. This is loop 75. Oh shit, bouncing onto the tether, kite just broke. Many pieces. Holy.
Flowchart. Makani M600 electrical safety after hard landing.
People are digging into flight data to say, okay, does this match what we expected? No. Do we need to change the model or change the actual kite? Should I do a reenactment?
Yeah.
Our rudder wasn't as effective as we thought it was, and we would have gone down a path of years of simulation
and thought it was good unless we got flight data to show, oh, look, when it does this, we're not getting the response we thought we were. We therefore need to make it bigger.
I think our PX09 is an example where the results are dramatic, but the solution is small. So even though the kite exploded, we're able to look at it, see what happened, make some fixes, and have confidence that it wouldn't happen again. One thing I've learned in controls is that the size of the solution is often unrelated to the size of the problem. What's pretty interesting is you can see like the original impact, and you can see where the tether is now. And so it must have like bounced. An extremely dramatic problem. The solution might only be a few lines of code to implement some simple features.
Crashing the kite was an opportunity for us to step back and see how far we'd come and how much we still had to do. Container henge had always been a temporary fix while we redesigned the ground station. Now, our new and improved ground station was ready to test. So while part of the team investigated the cause of the kite's mid-air breakup, we began hovering off of the new ground station in preparation for all modes flight at a new, windier test site in Hawaii.
This is the last week of testing, hopefully, before we go to Park Ranch. There's no more tests on the schedule after that, so this week is our last chance to test the hardware modifications we'll be working so hard for the last few months.
Just so you know, the wind is not good right now, so we're not spoofing it.
We were moving a lot more quickly than we had when we tested our first ground station almost 2 years earlier. But hovering under constraints again seemed painfully tedious, and we were eager to get back to crosswind.
We did operate on the panel today, which was so cool. Like, we took off from the bay in the middle of the panel, up, out, back in, coming down, getting close, but not quite there yet.
That kite and that ground station could break each other. Plus, we need that old kite to test, or we're going to be kind of SOL for a while until we get, like, another new kite that would be riskier to test with.
I want, like, let's get it going. We gotta move here. We gotta save the freaking world.
That's what's gonna happen tomorrow.
If there was no fear of failure, I don't think it would be worth doing, so I probably wouldn't be doing it.
Position control's really good. Everything's really smooth. Things are working out pretty well.
I'm feeling like they've pretty much done all the risk reduction that can be done here. And it's time to be strong and courageous and take the next big step. It's a pretty exciting time for Makani right now. We've got so many things that are just about to happen. We're just about to have our first flight at our new test site in Hawaii.
We are retrofitting these inverters here with energy dump system for extra safety.
Hawaii has been on the forefront of looking for ways to find more sustainable solutions to power production for a long time. And that, combined with the really great wind resource and the fact that we had tested there early in our development, made it a really compelling place for us to return to with our full system that would include our ground station and the kite put together for the first time.
So, in a very traditional way, we'll prepare this site. We're all gathered here, not only to be witness to the ceremony, but each and every one of you have an important part in this. We will be surrounded by many, many that we may not be able to see, but the presence will be here.
As a technology company coming from the mainland, we knew that testing our kite in Hawaii was an extreme privilege, and we felt a sense of responsibility to do it right and to do it safely and to respect the people and the place. We found a test site on ranch land near a gravel quarry. It was a place that would pose very little risk to people and planes and animals.
Just doing the work and doing a business here. Everything's working.
And we continued to do outreach to the community to make sure they knew what we were doing and could tell us if they had any concerns.
I really want to see it fly. Do a couple of loops. Well, not a couple of loops. We want to do so many loops, it becomes really, really boring.
As a career, I've always worked in energy, and I know that Hawaii has really viewed itself as a laboratory for how to find more sustainable and renewable energy because the people of Hawaii take their stewardship of the land very seriously. I think we just owe them a big thank you for letting us test there.
This is how future green technology should be. It's a vast grassland with some, hilly terrains. And then you're still, in the middle of the terrain, there's a white spot. And then we look closer, it's the ground station, and the kite is there. It's a kind of a combination of nature beauty with futuristic technology. I think it's awesome.
In the RPX program, we had a ton of firsts. It still didn't represent complete functionality of the system because the ground station wasn't there.
When we first flew all modes with Wing 7, we'd been scared of how our sky robot would get along with our robot on the ground. Putting the M600 together with a ground station was just as nerve-wracking. We had to hover a kite at full tether length to find out if the ground station could really perform all the operations needed to support crosswind flight. If it didn't work, we risked losing the kite and tether.
We did the dry run yesterday. Our ground station, the big scary robot, it's like a carefully choreographed maneuver, which part of the ground station rotates by 90 degrees and the tether has to swing through a certain region of it.
So, today we fly crosswind for the first time off the ground station. This is our first flight in about 6 months or something, so return to flight is a major goal, and landing successfully, safely on the perch.
No matter how confident we get in the improvements we've made to flight modes that have already been demonstrated, doing something for the first time is going to teach us a lot. And so the testing program that we have going on right now is going to give me a lot of data that is going to be super valuable. All modes is going to be huge.
Flying all modes with the M600 was something we'd built up to for a decade. Every bug we'd squashed, every late night we'd spent combing through data, every line of code we'd changed, every carbon bond we'd prepped, and every bolt we'd tightened was in service of this moment, combining the whole system.
I mean, we never know what's going to happen when we go fly, especially, you go unconstrained and there's no easy out, right? But we've proven that we can have things go wrong during crosswind flight, and it's kind of allowed us to move more quickly and take some extra risk, but it's also part of the game, right? We do that, we know that each time we go up, there's a possibility that it happens, and we prepare by having extra hardware to replace the pieces that are likely to break.
You're in ascend.
So they're engaged in that other line. Stay out. Everything's nominal. Ready? Looking good.
Ready?
Excel.
Ready. You're in Excel. I see acceleration.
Tether's tight the whole time.
Looks great.
Looking good.
You're in trans-in. Looking great. You're in crosswind normal.
Wind the box, twist tracking.
Looks good.
Good in the box. Small azimuth slew, it worked.
Makani so far has brought kite energy up at a scale that no one has done before. And it is something very impressive to see such a big kite flying so low from the ground. Seeing the whole system working together really makes you think this is possible. This technology might have some future.
We just keep setting goals and meeting them. There's no reason to believe that we can't keep doing that. Seeing the kite fly loops, it's that's the antidote to any sort of malaise. Go watch that kite fly loops and you'll believe that this whole thing will be possible.
32 degrees.
We're overspeeding a little bit right now.
Okay, we're still in crosswind prep transat.
There's the maneuver and hover transat. Let's go in.
Hover transat.
Okay, got a low point 4.
Tether tension about 8 kilonewtons.
Stop GSO2.
GSO2 we stop.
Log save. Log on main save.
Yeah.
It was like coming into being all on its own. That's how I felt.
It's a good day.
It's a good day.
Going. Okay, where we went up. Deep twist tracking. Okay. Yeah, we're good.
We were flying crosswind. We were doing it autonomously, without human intervention. But it wasn't enough. In the decade we'd spent honing our technology, wind turbines had advanced to the point where kites were no longer a cheaper source of power on land. Our onshore advantage had diminished, but there was still an enormous opportunity for kites to expand access to stranded wind resources offshore. We had seen this coming, and we'd already bet our future on offshore. Before we'd confirmed that our flight controls could prevent another mid-air breakup of the kite, and before we'd demonstrated flight from the new ground station, we had begun an 18-month sprint to show that our system would work in deep water offshore. We raced through flight after flight in Hawaii to demonstrate enough reliability to quickly transition our system to a buoy floating in the ocean.
In order to make the Makani technology successful, you had to demonstrate all of these things. So you can stagger them in time, but then it's going to take longer. Or you can try to solve them all at the same time, which is what we were trying to do. It's not because we were being naive about how engineering is done. It's because we didn't have enough time to do it methodically, one thing at a time. If Makani's technology was going to succeed, was going to be able to effectively, efficiently harness energy from the wind in a cost-effective way in offshore geographies, we had to fly off a floating buoy. We couldn't delay that. Like, that was going to take a long time to develop and to do. So we could get started right away, even though we were still in parallel solving other existential problems. Or nothing. Like, I was going to say or delay, but we couldn't delay, because then the problem we were working on solving was one that had to be solved immediately.
If you look at any of the research that's been coming out about the immediacy of the problem regarding climate change, it just becomes clear that we need as many good solutions as we possibly can. Having a low-cost, variable, renewable resource that can be deployed deep water would be of tremendous advantage to help solve that problem. So, I mean, I think it's an avenue for a lot of impact.
Most offshore wind turbines are installed in shallow water where they can be fixed to the seabed. But there is a lot of strong and steady wind over deep water. To reach that wind, turbines need massive floating platforms that are expensive to build and install. Without a huge tower, kites can get away with a much smaller floating platform, which means they are easier and cheaper to install in deep water.
It's just the sea surface cable that's untested, comms-wise?
Because we're not just going to go straight to spinning motors if we haven't checked comms.
A lot of things has to happen in the right order with very little people. But it's cool that we're talking about that today. So it's coming together. It's real. It's not a dream anymore.
We're going to Norway, and it's going to be just a matter of weeks now. What, like 26 to 33 days, according to the whiteboard behind me.
Seeing this beautiful lightweight structure, it almost makes my mind explode with possibilities. I look at that and I see all the deep water coastlines that are near population centers, and you really fundamentally see something that can scale and that can bring renewable energy to so many people. I mean, hundreds of millions of people. It becomes immediately clear to you when you go to Norway and you go to Stavanger and the Haugesund area. It's unavoidable to realize that this is a place where people do things in the ocean. Like, they're in the business of doing strange things in the ocean. And so it really felt like this is the place for us. I think the Norwegian people have a really great cultural fit with Makani and what we're doing. People are comfortable with a little bit of risk, with a lot of uncertainty.
We really constrained ourselves to work with the technology and the existing stuff that Makani had. We've been able to basically take our onshore testing and move it offshore. We've pushed it together a little bit more and put it on a barge.
Yeah, we're like showing up and it feels like a, fully fledged test site where it's mostly things we totally know about, just in a different place, which is really cool. But there's been a big effort to get this ready.
Generally, doing things offshore at sea is just harder. The environment's way harsher.
There's a whole slew of things that once we sort of cast off from shore, you can't really fix. So if one of those things goes wrong, then you're sort of between a rock and a hard place. Getting to the spar that our base station's sitting on and our kite is at is hard and could be dangerous in, high seas or bad weather.
Joy. Yeah. Yes.
I'm just really happy to see it, and obviously a lot of people have been putting in a ton of effort to get there, and it's just kind of shocking that we're there and might see something really cool happen in a couple weeks.
The spar buoy is called Havdraga 1. Draga means kite, and it also means dragon. So it kind of has this double meaning that I really like. We're 2 days until tow out. We've been preparing for 18 months.
There's a lot of work done in the last 9 months or year, of course, but a lot in the last 2 weeks since we arrived here, just to do the final checks on all the system, dry run the kite, and now finally all systems are go, people know their role, and we're going to lift and put it on the panel. So we're going to show the whole world that, hey, we have a kite ready to fly in Norway.
Normally, deepwater offshore wind programs take many, many years to develop.
Over the last 18 months, all these steps came together. A plan was laid out that looked, I would say, bordering on impossible. Barely feasible, if everything went well.
Behind me is Sleipnir. We are 2 days until tow out, and the lift went beautifully.
The whole team at Makani, once we kind of wrapped our mind around the fact we were going to try to do this, and everybody started pulling together, the whole is greater than the sum of all the parts. All these teams working together have put together something that we individually might have thought, this is impossible.
For some of us, like Crystal and Alan and Luis, you guys just are like handing off the kite and now hoping that everything you touch works, so thank you guys for just getting to this point, how big of an accomplishment this is. So first, thank you guys, this is amazing.
Offshore seemed like a fantasy not that long ago, but it is very real today. The tow out has been set in motion.
Only half a year had passed since our first crosswind flight from the ground station in Hawaii. And now we were halfway around the world getting ready to fly crosswind from a moving base station floating in the ocean. We were used to pushing hard to pull off increasingly complex feats of engineering. And this time we had surprised even ourselves. Most of the deadlines we'd sprinted towards over the years were driven by meeting technical milestones that would make it clear our technology was worth funding. This time was no different. We'd left X earlier in the year to become an independent company, and we'd partnered with Shell to test our kite offshore. To guarantee a future for our technology, we needed to demonstrate that it would work in the environment where it could have the most impact. After a full spring of flight testing in Hawaii, there were only a few weeks of summer left in Norway, and we knew we would probably only get one shot to fly offshore before the sea state would be too rough to test our kite.
We're not just launching and landing. Now we've got a buoy. It's a floating foundation just tethered to the seabed with one little cable. It has to know exactly how that buoy is moving in order to be able to land.
So it's too complex to be analyzed using only math and simple expressions. We need a full simulation. Well, the first time anybody's done something like this, I've never seen a buoy like that move the way we're gonna make it move.
Soon we'll have a moment of truth. The cable has been connected mechanically, and I believe they're working on connecting it electrically. So, let's see, it's past 8 p.m. on Sunday. We're hoping very much that we can turn on the kite and make sure that everybody still talks to us, get our first measurements of the buoy motion and the GPS performance. So far, nothing is broken. Continue to hook up the sea surface cable. I've never seen so little wind. It's all working.
We're going to work. We're going to fly a kite. The spar is probably 15 minutes away. Just a normal routine, but at sea. So and we're just commenting on the commute. Like, this is a different commute than we had either in China Lake or Parker Ranch, but it's pretty cool to commute by boat like that in the morning. It's a beautiful sunrise.
I think a successful test is any test that actually launches. I think just seeing how the launching dynamics work compared to our simulation is a huge step forward. Seeing how the kite interacts with the buoy as the buoy moves and the kite tries to track it even just a few meters away will be super valuable data. That's the first level of success. Everything past that is gravy. Our simulations show that launching is not that hard, so that'll probably go fine. Reeling out will probably go fine. Trans-in will go fine. Crosswind will go fine. The biggest challenge in the test will be, of course, to the land.
Gonna fly! Wind's supposed to come from there. Kite's in the right position, ready for it, and it could happen. Yeah, the forecaster is for like a nice building breeze.
The thing that's amazing to me about making things real is what you learn that you can't imagine.
There's always that healthy voice that tells you, are you sure you've looked at everything? Are you sure it's gonna work?
Tomorrow, we're flying in Norway, and it's early morning Alameda time. So we expect the masses of very excited engineers to show up at midnight with pizza and breakfast to see the flight.
What time is it?
Game time. Game time, that's right.
Yeah, I'm gonna get the throttle right below 0.8. Oh god. Ready? Looking good here. Going.
Gain is ramping. Gain ramp is complete.
The altitude's dropping a little, but it caught itself. Good.
Beautiful, beautiful. No saturations. Tension is 9.
Level 1, observe. Level 1, the elevation angle is bad. 40 degrees, I see.
What?
So I read elevation angle of 39.
What did it look like visually?
It looks like we're still above the perch, so I'm gonna try to land, okay? Then we can talk about this. 7.
The tether elevation angle
6.
wasn't reading correctly.
Elevation angle is still bad. 4.
I think we're just high enough. We're just high enough.
1.5 meter payout. 1 meter payout.
Rattles made it over, hooks are over.
50 centimeter payout. Watch for the park sensor.
It's probably gonna go negative a little over.
Yeah.
We're over the
You're on the
perch.
perch. Yeah, over the perch.
Descend. Starboard hooks in a tooth. Coming down. Port hooks down. What just happened? It's really close to falling off. It just skipped a bunch of teeth. Did we gain ramp?
Yeah, gain ramp is down.
Okay, hold on. Let's go down. God.
I can stop the ground station if you want.
We need to go back.
Is the starboard hook in the sawtooth?
It is.
Okay.
We found the error, fixed it, and prepared to launch again.
Threshold. Sounds good. And everybody ready?
Ready.
Ready.
Okay. 3, 2, 1.
Bottom up swell.
Launch.
You're in ascent. Okay, you're at 0 elevation angle, you're in payout, and the engagement sensor says engage.
Release the winch.
Winch velocity is increasing.
Clear.
Elevation angle
There
is
she
stable.
goes.
9, looking good.
GPS agreement improved greatly.
Alright, altitude's 100.
Payout crossing 300-ish.
Azimuth will behave on the ground station. That's good.
No
No
gates. Crosswind monitor is on.
Good to go?
Continue and ready. Throttle above 0.8.
Okay.
Is it good on inverters? Yeah. Inverters look good.
Brick cell.
Back to the playbook. Move forward.
Looks beautiful.
Good.
Perfect.
D2 is following.
Perfect. Crosswind normal.
That's a nice gradual return into this here.
Alright. D2 is looking
Making
good.
the turn. Arrow angles look super.
3 o'clock.
Super. Wind is 9.7.
Oh, look at that blue go. 9 o'clock.
Nazi error looking good.
Arrow angles great. 90.
Can you guys believe that? We're flying across river in the North Sea. So cool.
You know, a machine achieves perfection, not when there's nothing left to add, but when there's nothing left to remove. Like a standard horizontal axis wind turbine just looks very natural because its design has evolved to this state of like near perfection. But it wasn't always that way. It was at one point a radically new technology that was kind of like Makani is now.
The word I have is like, you know, it's like 横空出世. It's like something you feel that it's never been there, but it just emerged suddenly. At first, you don't know what it would do, but once you see it, you know, take off and function, you say, yeah, this is something that it's born to do. It makes me feel the ocean is smaller than it is, but just because we are looking at it from such a long distance away.
Yeah, it looks perfectly boring out here.
Personnel transfer.
Oh, is the sea building?
Yeah, the wind is holding steady, the sea's building a bit.
In which? The wind swell? It looks like the southwest is dying.
The wind, they're worried about the wind.
Okay. We'll trans out at 1:30.
Yeah, that sounds good.
Perfect. Not the next loop. The next one at the top, we're going to prep trans out. Sounds good. Okay, ready for prep trans out?
Ready here.
There it is.
That radius land 160.
Okay, 6 o'clock. Slow it down hard and flare. Gentle. It's a different angle. Yeah, we were pretty high, so we're coming down.
Saturation.
So you want to stay preference for that? Yep. The buoy looks already.
Vessel angle is damping.
Yeah.
Vessel position is still quite a bit displaced.
Rolling. Robbie, what's the roll angle? Increasing tension?
30, 40.
It's piling over.
Yes.
Pitching back.
Minus 70.
Whoa,
Tether pitch is
throttle's all the way
100.
up.
Oh, tether pitch is 99.
60 degrees inhibition angle. Come on, come on, come on. Stop everything. Okay. I don't know what happened. It's stable. Can you guys do the checklist? I'm gonna go do the controls. Yes.
Well, we had a pretty good day. Didn't quite stick the landing in the second time. We will be crunching data and learning from this test flight for a year at least. The kite landed in the ocean. It did not come back and land on the perch, which on the surface of it, sure, okay, yes, that's a failure. But I can tell you what would be an even bigger failure, would be failure to launch. We needed to get moving, and we needed the goal of a flight to learn what we need to know as we design the next version of our kite and as we iterate. All those things that we were scared of, we now understand better. And all those things that we didn't yet know about are now at the front of our mind. Was it worth a kite? Absolutely, it was worth a kite.
I'm still confused and surprised by Charlie's enthusiasm. Yeah. He sent a couple of emails and he's up there, but
yeah, he's still up there.
I've seen this, but
yeah,
it's not nice to see. No, it's not.
The wing harness alone, which is just POF and copper, is what's holding the mass, what held the mass balance tube on.
Do you have feelings about building stuff up just to get it crashed?
Trying to make me cry right now. You know what? I was really ecstatic to see the kite fly, and I watched it for the whole hour that it flew crosswind, you know, and that was amazing. Like, who can say they were a part of achieving something so beautiful, you know, and heart-wrenching at the same time.
When our kite is hovering, in order to maintain the right angle, we need to have the tether be at an appropriate angle, ideally horizontal, and there has to be enough tension. But if the kite is too high, or if it's too close to the ground station, we can start to drift, and we didn't have a very good way to recover from that.
Many people worked super hard to get this thing ready. And yesterday we flew our big great flight, and we finished with a big finale, and now we're starting again, I guess. We demonstrated that kites could operate in deep water, where only a handful of wind turbines had ever been tested. Our test in Norway hadn't gone perfectly, but it had shown us what was possible, and on an incredibly short timeline. Watching the kite fly over the open ocean, it wasn't hard to imagine kites flying in concert around the world, powering coastal population centers with cheap, renewable energy. It felt like we were really getting close to something that could make a difference. Meanwhile, another part of the team was already sprinting towards another milestone to redesign the kite in a way that would produce more power.
It was a 3-month project. It was called October Kite because the end of the project was October.
Take our the innards, which are really quite impressive and awesome, and then just transform them into the new kite. So the analogy I would use is it's basically like a re-wing of a design, which is, I think, a pretty standard thing in aerospace. So we're just going to take it all and just transfer it to a new piece of carbon. So that's the idea.
The October Kite team came up with a simple design that would increase wing area for greater lift and more power production. It would be ready by early 2021, and in the meantime, we would keep learning with the M600.
When we got home from Norway, we took the lessons we learned there and we fired up the simulator, started thinking of ideas, and began implementing fixes for what we observed in Norway. And then the next step was to fly again and test those changes.
That looks legitimately good, Robbie. The butter, some sugary jam on good bread.
You feel better?
Robbie either fasts or just goes for it.
Feast or famine.
I'm in his camp. That's how I roll too.
The wind forecast shows, actually both wind forecasts show wind going northeast around like 10 or 11 o'clock. It's kind of ideal. It's not a super strong trade wind pattern like 2 weeks ago where it's blowing 15 to 18.
We would spend the fall and winter flying in Hawaii and testing improvements to the controller before returning to Norway next summer, when the weather would allow us to go out to sea again.
So I think nobody really knows, first of all, if it's practical to have an energy kite, and the right way to do it. And so there's a lot of questions that need to be answered, and some of them are super interesting to me. And the goal of the company is to prove that the technology can be developed and that it would make sense to do it. So I think our mission right now is to prove that we can do that.
Do you have a They're engaged, stay out.
We'd flown offshore, and we had a promising new kite design. But in the years since we'd left X, we'd failed to find the investment we needed to carry our technology forward. Designing and building a new kite would be expensive, and so would another test campaign in Norway. And then, after that, we'd have to spend years dialing in the reliability of our system. We felt like we'd solved the miracles that were needed to make power from kites. But what we were doing was still experimental and still risky, and the road to commercial viability was proving too long. After 13 years of setting goals, meeting them, and setting new goals, the end of our path was suddenly, glaringly, in front of us.
So these people in the, I think, 1940s came up with a design, like maybe windmills don't just have to pump water, maybe they can make electricity. And they gave it an honest shot. It was like a big engineering project, and it was successful. It made power, but ultimately it was shut down because the price of electricity from this pioneering wind turbine in the 40s was like, something like 50% more than the price of coal at that time. And so it was shelved for something like 30 years. It's phenomenal to me.
At the terminus of this technology, like when all is said and done, 60 years from now, we've worked out all that we need to do to be able to control the system. We've worked out all the ways we can bring the cost down. We've got all the reliability. It is a more compelling value proposition. Like, it's significantly less mass, and you don't have all this extra stuff to just harness the power.
This level of innovation, I really haven't encountered it anywhere else. It is important to try new things, and sometimes it's a radical new thing. You know, it does take a lot of courage. It's the value of exploration. You don't know what's going to come out of it.
I think we have to be audacious because we have children. And I mean it really in two ways. You have to be audacious so that children have astronauts to look up to and heroic engineers, and they get to see people working on things that are hard and see the struggle. But I also think we have to do it for our children because we owe them a planet that works. And the timelines are getting shorter, and the level of effort is not getting any less.
I feel like sometimes people think of Makani as a company of many hundreds of people because we do such amazing things. And if you really look through it, we're only a few tens of people doing all the good work that led to those crazy experiments.
We were flying a kite, and it was delightful, but it was also for helping advance the renewable energy, just for being a little bit kinder to the world. Did we succeed in making flight boring or testing boring? And I think not. Like, sadly, but also like very joyfully not. It was never boring.
We spent 13 years fighting to harness energy from the wind with kites. Our team grew up, babies were born, and the world changed around us as we remained focused on an effort we hoped would make a difference. We took an idea and carried it as far as we possibly could. While we didn't achieve everything we set out to do, we learned to move beyond conventional thinking, solve massive problems, and redefine our notions of what is possible. When it comes to climate change, we can't afford to stand on the sidelines, and we can't wait for a surefire solution to come along. We have to plunge into solving problems that seem impossible. We have to risk the chance that we will fail, because that is the only way we can possibly succeed.
Hringir, það nóg. Örlítil gola, allt svo ljótt. Fyrir tíma út ég fer. Skýjahjúpi sé sem á strönd. Svo sé ég sebrahest með bara eina rönd. Ég sem ætti að sjá haf og lönd. Da skugga skimar fólk sem að vill heyra hljómanna flögra sitt eyra blístra, brosa og biðja meira
Sweeping the desert, an endless but noble task for the future of Energy Kites. I don't think this is really a poem so much as the beginning of a novel.
Maybe a dramatic speech.